electron. Okay, first of all, let me write the topic. We are going to find the equation for magnetic dipole moment of a revolving electron. When an electron revolves in its own orbit, it is a charge. Okay, electron is negatively charged, so it can be compared, or it is the current loop. Okay, when an electron revolves around the nucleus, that electron will act like this orbit acts like a current loop, because electron is moving, so there will be current produced. So that also becomes, now when there is a, in the previous class I have told you, a circuit loop acts like a magnetic dipole. Now what we assume over here is electron has got charge E, it is moving with the speed v. Okay, the speed of electron revolving is v. It's moving in an orbit that is anti-clockwise. The movement of the electron is anti-clockwise. So if the movement of the electron is anti-clockwise, by right hand thumb rule, what we know is if it is moving anti-clockwise, okay, clockwise the magnetic dipole will be upward, anti-clockwise. Okay, if it is moving anti-clockwise, the magnetic dipole movement will be downward. So the magnetic dipole moment will be acting downward. This is the direction of magnetic dipole moment. Now you have to find that. Okay, now when an electron revolves around it in its own orbit, it produces current. So current I is equals to, the formula of current is I is equals to charge per time. So what is the charge over here? Charge of electron is E, and capital T will be the time period for one revolution, or to complete one revolution, T will be the time period. Now over here time period, let us find what will be the equation for time period. For one time period is traveling one complete revolution. So the formula for time period will be, it is a distance, so distance is equals to, speed is equals to distance divided by time. The distance traveled by this electron divided by its velocity. So it will be distance divided by velocity or speed. So the distance divided by the distance covered by the electron, okay, will be, suppose the radius over here is r. Distance covered by the electron will be 2 pi r. That is the circumference of that orbit. Okay, circumference is 2 pi r. That will be the distance traveled by the electron. Velocity or the speed is denoted by v. So this is your time period. Now let us put this time period in this equation over here. So I becomes, your I becomes E divided by 2 pi r. This will be the current. Now this is the current generated when electron moves in its own orbit. Now next what you have to find is, you have to find the magnetic dipole moment. Magnetic dipole moment, previously I have given you the equation of magnetic dipole moment is I into A. I is the current, A is the area covered by the electron, or area covered by the electron while revolving. So the area of a circle is pi r square. So your A is pi r square. Now let us put the value of I and A over here, we will get M. So M becomes I into A. I is EV divided by 2 pi r into area is pi r square. So this and this gets cancelled. Magnetic dipole moment becomes EV divided by EVR divided by 2. Equation number 1. So this is the magnetic dipole moment of a revolving electron. Now whenever a charge particle moves in an orbital circuit, what we have to find out is, and also find out the orbital angular momentum. You have studied about linear momentum. Linear momentum was when an object is moving in a straight path. Now orbital angular momentum is when an object is moving in a circular path. So over here we have to find orbital angular momentum. For that, divided by G. So the formula for orbital angular momentum will be linear momentum into radius of the orbit. Unlike linear momentum, in orbital angular momentum, what thing is continuously changing is the radius is continuously changing. So orbital angular momentum is equals to linear momentum multiplied by radius of the orbit. So now linear momentum, if you remember, the formula of linear momentum is m into v. M is mass of the electron, v is the velocity or the speed of the electron. That is linear momentum multiplied by radius of the orbit is r. So your orbital angular momentum becomes mv/r. Okay. Now this would be question number 2. Another thing what you have to remember is your orbital angular momentum is always perpendicular to the plane of the orbit. If this is the plane of the orbit, okay, this is the plane of the orbit, orbital angular momentum is always perpendicular to that. Okay, it's always perpendicular. Okay. Now dividing equation 1 by 2. We will divide equation 1 by 2. Dividing 1 by 2. So m divided by g is equals to EVR by 2 divided by MEVR. Okay, now divide these two equations. After dividing, what we get is, after dividing the two equations, what we get is, we get m by j is equal to, after cancelling the terms, what we get is, we get E divided by twice m E. VR gets cancelled, it becomes E divided by twice m E. Now this is the ratio of magnetic dipole moment and orbital angular momentum. Or this ratio is also termed as gyromagnetic ratio. Okay, it's also termed as gyromagnetic ratio. Now, in actuals, m is minus j into c by twice me g. Now, I have written this minus sign over here. This signifies that magnetic dipole moment and orbital angular momentum are opposite in direction. Okay, are opposite in direction. Now the unit of magnetic dipole moment I have already given you, that is ampere meter square or joule per Tesla. Okay, this is for magnetic dipole moment of a revolving electron. This will be the final equation. Okay. Now the next topic which I am going to discuss is magnetic field of a magnetic dipole. Okay, magnetic field of a magnetic dipole, and that magnetic dipole will be your bar magnet. Derivation is not required over here. Only what you need to remember is the formula and the different conditions. Magnetic field of a magnetic dipole. That magnetic dipole is your bar magnet. Any magnet is actually a magnetic dipole. Without two poles, there is no magnet. So first is to find the magnetic field at the end point or at the axis of the magnet. So first of all, we need to find the magnetic field at the end point or at the axis of the magnet. So let me draw a magnet. Similarly, we'll compare this to the electric dipole. Okay, so we'll write the similar notations as we have done in electric dipole. This electric dipole and the electric field at the axis equatorial point we have done in the first chapter itself. So I hope you still remember that, and we are going to compare the equation of magnetic dipole and electric dipole. So now this is North and South pole. In the center will this distance will be L, this half distance is L. Together the distance or the length of the magnet is twice L. Okay. Now we assume that we take a point P and we find the magnetic field at this point P. Okay, magnetic field at this point P. Now what we know is magnetic field originates from North Pole, it goes to South Pole. So at this point it will be like this. The direction of the magnetic field will be this side. It is from north and it moves towards south. Okay, twice L is the length of the, please note it down. Okay, twice L is the length of the bar magnet. M will be your magnetic moment or magnetic dipole moment. We are assuming this setup, this whole magnet, this thing to be in vacuum or in air, which has got very less resistance or permeability is fixed. So now the equation of the magnetic field, no derivation, just equation is there. So equation of the magnetic field at this point P due to the bar magnet having length twice L is equal to, that will be your mu naught by 4 pi, okay, twice mr divided by r square minus L square to the power square Newton per ampere meter inverse. Okay, this is the equation. Now please refer to the first chapter, flip your books and try to compare it with the electric dipole at axial point. This is a similar equation. What is not there? Instead of this mu naught, you will get epsilon naught, and instead of m, that is magnetic dipole moment, you will get electric dipole moment, that is P. Only that is different. Rest the equation is similar. That is why the derivation of this is not required. But please do remember the equation and please do compare the equations. It will be easier for you to remember. Okay, now in that derivation also what we have considered is, okay, sorry, I haven't told you what is your R. R is actually the distance from this point to the point P. The distance from the center of the magnet till the point P is the distance R. Now when your L is way more smaller than R, when the magnet is very very small compared to the point we are measuring the magnetic field, then that L can be ignored. So P becomes mu naught by 4 pi. Okay. If this is ignored, then that 1 R gets cancelled. So only there are 4 R's, only 3 R will be remaining to be twice m divided by R cube. Okay, this is ultimately what you get. Magnetic field at the axial point of a magnet. Okay. Now similarly we will find on the broad side or in the equatorial point which is in the electric field. We will find the second one, that is broad side on position. Okay, over here we take a bar magnet, South Pole, North Pole. Okay, South Pole, North Pole, center is O. The total length of the bar magnet is twice L. We'll take a point P exactly at the center, and over here we'll find the magnetic field. The distance from this point to this point is R. Okay. Now the equation over here will be, first of all let us see the direction of the magnetic field. Direction of the magnetic field, it is from north towards south. So it will be a ring-like magnetic field. So at this point, it will point from north to south pole. Direction of the magnetic field, north towards south. Okay, now the equation B is equals to mu naught by 4 pi. Okay, mu naught by 4 pi m by r square plus L square. Okay. This is what we have. Okay. Similar equation for electric dipole moment at an equatorial point. Now similarly, when this distance r is way greater than L, we ignore that L. So it will be mu naught by 4 pi m by r cube. This is what we get. This is for the equatorial point of the magnet. Okay. Now the next topic which we are going to discuss today is torque on a magnetic dipole. Okay, so we'll discuss this topic. It's a very short topic. Okay, we just discussed that. Now on this topic, we are going to derive the torque on a magnetic dipole, that is a bar magnet. We have discussed this type of a topic various times, so please don't get confused. Now I have told you that when we bring a magnet in a uniform magnetic field, there is a magnetic field, a space region of a uniform magnetic field, we bring a bar magnet. Then what happens? The bar magnet will itself rotate. Okay, the torque will be formed over there and it will align itself parallel to the magnetic field. So if there is a magnet, I bring it over like this, it will rotate and align itself parallel to the magnetic field. That is what happens when you bring a magnet in a magnetic field. Now, I have told you that a solenoid is a type of a magnet. So, vice versa, a bar magnet also has to act like a solenoid. So, what is a solenoid? It is a small ring, small ring kind of a current loop over here that forms a bar magnet. So, similarly, a bar magnet also is a small current loop. Okay, a bar magnet also acts like a small current loop. So there are infinite number of current loops which forms a bar magnet. So now the torque on a current loop done in the first topic of this chapter, that was IAB sin theta. Sin theta was the angle between the magnetic field and the axis of the solenoid. Over here it will be axis of the magnet, that is theta. Now over here what we can see is in a bar magnet there are infinite number, n number of current loops. So it is not only one, it is n number of I, A, B, sin theta. This is the torque. Now what is NIA? NIA is magnetic dipole moment. Just replacing NIA by M. B sin theta. So this is the torque. So suppose you want to remove the sin theta, what we can do is directly write M cross B, because sin theta is a cross product. So we can write cross. Now with this, what will be the condition for maximum torque? What will be the maximum torque? When will be the maximum torque experienced by this magnet? It is when theta is maximum. So when sin theta is maximum, when it is actually 90 degree. So when sin theta is sin 90 degree, then it is maximum, or this becomes 1. So it will be, if this becomes 1, it will be M into B. This is the condition for maximum torque. That is, the torque will be maximum when sin theta is 1 and this becomes M into B. From here, B is torque maximum by B. Okay. Magnetic dipole moment is equal to torque maximum by B. We can also find from here itself. Okay. Now when this will be equal to torque maximum, when the magnetic dipole moment will become torque maximum, when B, or the magnetic field which over here, is equals to 1. That point, torque maximum will be a magnetic dipole moment. So magnetic moment is numerically equal to the torque acting on the magnet when held perpendicular to the uniform unit magnetic field. So when this axis of magnet, when it is held perpendicular like this, okay, perpendicular to this magnetic field, at that point this will experience, the bar magnet will experience maximum torque. Okay, perpendicular means 90 degree, the maximum torque will be experienced. When will be the minimum torque? The torque will be minimum when it is already parallel. When angle is already 0, the torque will be minimum. Torque will be maximum when perpendicular or 90 degree. Torque will be minimum when 0 degree, when sin theta is 0 degree. So logically, if you can imagine this, when a bar magnet is kept on a magnetic field, brought near to a magnetic field, what happens? It will align itself parallel. So when will it align itself parallel? When it is not parallel, then only it will become parallel. So when it is 0 degree, no force will be acting on this one. When it is 90 degree, the force or the torque will be maximum. Okay, this much for today. Now the next topic will continue in the next class, and I hope that topic will be the last for this particular chapter. So thank you very much. We'll continue in the next class.